All right. What I'm going to talk about is crystal structure prediction. It's for earth sciences and for material sciences and for physics and for chemistry. This is a rather new and booming area of research. Research which is quite fundamental in many, many ways. So I will tell you a little bit about how it works, very briefly what we have done for minerals, for materials, and a bit of new science, and what we actually need, what we can do, what we can contribute to the community, and what we can hope to get from the community. By the way, once I said the word community, it gives me great pleasure to realize that now our dream of creating a community is becoming true. Thanks to Renata, with whom we have been discussing this for a long, long time, Don Widener, who has been supporting us for a long, long time too. Our community of computational mineral physicists, as most of you surely know, has been fractured for a long time, and it was not really a community, it was a set of individuals who were doing research pretty much on their own, instead of having joint infrastructure, joint meetings, and so on. And I hope now we will be able to change these things. By the way, before I go on with science, I want to make another comment. Why do we need all that? One simple reason is that if you look at the leading codes that exist in our field, codes for first principles calculations, you will immediately realize one thing, that all of them come from Europe. Quantum Espresso comes from Europe, WASP comes from Europe, Wien comes from Europe, Crystal comes from Europe. Name me whatever other leading code, it comes from Europe. Europe has comprehensively beaten us on all points. And one of the reasons for that, I believe, is that instead of doing science, we run grants. And we spend 99% of our time writing grants with a success rate of 12 or whatever percent. We waste our time. While Europeans are writing codes that we are then citing. Yeah? So I think that initiatives like that are a good reason for us to change the situation, and the situation really needs to be changed dramatically because it is rather humiliating for American society to rely entirely on the mercy of European funding agencies, if you wish me to put it in these words. And European funding agencies are doing things in this sense correctly because they are providing long-term, reliable funding for code development in Europe. And we rely on Mercy on NSF every 5 years, or whatever, 2 years, or whatever crisis, stimulus package, heaven knows what other garbage we rely upon. That really needs to be changed. Anyway, back to research, back to science. What we are concerned with, I think our code is perhaps the only US-developed code that is leading the way, although it started in Europe too. So it is actually half European. Anyway, what we want to do is to enable computational design of new materials and computational discovery of new minerals. It all started for us with post-perovskite, when it was exceedingly clear that the discovery of one new crystal structure changed entirely the whole playground. Yeah? Just one crystal structure. And then immediately the question that occurred to me was, well, I had this question at the back of my head for a long time, but then when post-perovskite came up, that was a pressing need, not just a question. How to discover new post-perovskites systematically on a daily basis on your computer. Not relying on private communications from Tokyo, as was Renata's case and my case too, but relying on your intelligence and intelligence of your software. What has been done before was the fortuitous trial and error discovery of new materials and new minerals. Cook and look approach, yeah? And the pioneer of that was Edison, who pioneered this trial and error approach, and who even was brave enough to say that he has not failed 10,000 times, he has just found 10,000 ways that won't work. And my lifetime is probably too short to, and my patience is too short to wait 10,000 failed attempts before making a good discovery. We want to do it systematically here and now. Just a reminder that computational science is not just some little tail on the body of experimental science. It's a new third pillar of modern science, in addition to theory experiment, and computation. Computation being different from theory and experiment, somewhere in between the two. Okay, so for that we need good hardware. We know that the power of hardware is increasing dramatically, and that means one simple thing, that to stay competitive, we need to update our hardware every couple of years. There is no way to remain competitive other than that, and we need good software. And to have good software, we have to develop it here rather than buy it from Europe. Yeah? Okay, are crystal structures predictable or not? The problem is to find the global energy minimum, configuration of atoms that has the lowest possible free energy. And you could, of course, try all possible combinations of atomic positions, all possible combinations of cell parameters, and then see which one has the lowest energy. If you will do that, you will be stuck in an exponential wall. The problem will become exponentially harder as you increase the number of atoms, and already for 10 atoms, you will have to deal with 100 billion different structural variants, which will take about 1,000 years. And as you go to modest sizes like 20 atoms in the unit cell, you will have to wait longer than the age of universe to go through all possible structural variants. So that's not a way forward. One of the ways forward that we have developed is an evolutionary algorithm that shortly after it was published was praised as not evolutionary but revolutionary. I will tell you a little bit about that. So we know how to compute energies, and all we have to know is how to generate good candidate structures. We don't want to sample all possible structures, all these trillion structures. We want to find a shortcut to the most stable one. People have tried random sampling, simulated annealing, metadynamics, minima hopping. These are the 4 most popular methods. I don't have time to comment on them. Okay. So I will tell you a little bit about our method and a few results. Okay. One method for global optimization is hill climbing, or we could call it random sampling, as it is frequently called. So I will use a cartoon borrowed from an Australian colleague, Richard Clegg. We're talking about finding the lowest energy, so it's like the lowest valley on a landscape. In Australia, they see things upside down, so what is a valley for us is a mountain for them. What is minimization for us is maximization for them. You add here a typical inhabitant of the 5th continent, and here you go. The problem transforms into finding, with the help of a kangaroo, the highest mountain, Mount Everest. Random sampling would be dropping the kangaroo somewhere on the surface of the Earth and giving it an instruction to go uphill. Going uphill or downhill in our hemisphere, meaning to relax the structure. Yeah? So you drop some random structure, you relax it, compute the energy, and repeat it many, many, many times until you find the optimum solution. This is usually very time-consuming. But this approach, by the way, it has one advantage, that it is perfectly parallelizable. You can drop 1 trillion kangaroos at the same time and compute their energies in parallel. So you can parallelize it over as many CPUs as you want. The question is that it's a waste of time, and from the point of view of a funding agency, I would not fund such overexpensive approach. Another approach is simulated annealing, which is similar to the previous one, except that you make the kangaroo thoroughly drunk. It still tries its best to go uphill, but it falls from the hill. It gets lost, it goes to a forest, to a lake, to a sea, it can drown, it can do all sorts of things. But sooner or later, this kangaroo, if it survives, of course, will climb on top of Mount Everest. Sooner or later, it will happen. Probably later, but will happen. Okay, another approach, and this is an approach that we've been developing, approach that is actually very popular in other branches of computational science and engineering, is based on evolution. We drop a set of kangaroos, more or less randomly, on the surface of the Earth. We allow them to create kids. Oh yeah, we make each one of them go uphill, on top of nearest hill. Then we evaluate their quality. The lowest ones, those which are not good enough, are eliminated with the help of good hunters. Those who are relatively fit are used to produce children. And for reasons of decency, I will not show you how this is happening. Then we evaluate the children and the parents. Then we again invite hunters. And this evolutionary pressure pushes the population uphill until you find Mount Everest. And this procedure turns out to be quite efficient. In terms of energy landscapes, this is how it looks. This is an energy landscape actually of a real chemical system, gold-palladium alloy. Blue regions correspond to low energies. Red regions correspond to high energies. These circles are currently sampled points, currently sampled structures. So you can see that the first generation is random and it covers more or less homogeneously the landscape. In the second generation, the density of sampling of low energies increases. And this tendency strengthens with each generation until you find the global minimum. So the game is won, yeah, in just a few steps. It is crucial how we produce children from this, from parents of our population. Let me not describe too much these technical recipes. What I want to say is that we have an initial relatively small population, let's say 50 structures, maybe 100 structures. And from the point of view of hardware, you can easily parallelize, and our code is parallelized over this population. So you can do 100 energy optimizations at the same time. Each one can be parallelized over, let's say, 32 CPUs if you have larger system, maybe over 100 CPUs. Multiply 32 by 100, you easily get a range of thousands of CPUs of parallelization. Yeah? If you have a very complicated, challenging case, it can be even up to maybe 10,000 CPUs parallelization. Okay, this is a simple comparison of random sampling where we randomly drop atoms and then relax the structure over and over with evolutionary simulation. So random simulation, you can see it samples the same energy distribution all the time. It doesn't learn. And after 120,000 steps for magnesium silicate with 40 atom supercell and cell parameters of post-perovskite, even after 120,000 structural relaxations, you do not get post-perovskite. Yeah? With our method, you get post-perovskite after just a few hundred steps. This is really very short. And the key here is learning. The key here is, the key here is learning. We start with the same energy distribution as for the random sampling, and then we learn how to produce lower and lower energy structures, and then bang, the ground state comes. Okay, so we have relatively decent parallelization, well, actually excellent parallelization over thousands of CPUs, and we have very fast performance. If you increase system size, complexity of such problems goes up exponentially, but you can see that the exponent is still very shallow. And even for 80 atoms in the cell, we produce a ground state in a reasonable time. Okay, that I will skip. We have extended this method to nanoparticles, surfaces, other types of cost functions, not energy, but let's say properties of various types. So now it is possible to predict structures of nanoparticles, which has interesting technological and environmental applications. For instance, for MGO, it turns out that two configurations are very competitive. One reminiscent of a fullerene, it's hollow, and another one reminiscent of a nanotube. And nanotube somehow wins. Who would expect something like that? Yeah? So this is a field, this is a new field which is full of new discoveries to be made. Yeah? And crystalline surfaces have perhaps even more exotic structures than that stuff. And we're working in that area too. We have produced quite a lot of publications in the last 5 years based on this method, structures of new elements and new chemical bonding under pressure, compounds possessing superconductivity and super hard properties, somewhere here, yeah, super hard properties, new minerals, new materials of giant planets, and so on and so forth. Okay, some new results, so new or old results. One of the first results was actually on calcium carbonate. What we found was, okay, this thing doesn't really work. What we found was two new crystal structures, post-aragonite, which is now found in a good dozen of compounds experimentally, and which was verified already in our paper. And a new paper, and a new phase where carbon is tetrahedrally coordinated rather than threefold coordinated. And this phase was verified 2 years after our prediction. Actually, during these 2 years, I can confess to you that I had sleepless nights because it was my first